So this is a sort of illustration of this point, and I haven't showed you the code that generated it. But what this is the distribution of F statistics that I obtained by doing 1,000 experiments, not actual experiments, 1,000 simulated experiments in R. So for each of the 1,000 experiments, I sampled n equals 10 3 times. I sampled 3 groups of 10 from the same population. In fact, the identical population. A Gaussian with mean 100 and variance 15. And I sampled randomly 10 values, group 1, 10 other values, group 2, 10 other values, group 3, and then I computed an F ratio. And I set that aside, and then I did it again. And I sampled a new set of 10 values 3 times, and computed another F ratio. And I did that 1,000 times. And this is a distribution of those 1,000 F statistics. So this gives us an empirical distribution of what F should look like under the null hypothesis. In a situation where I sample 3 groups of n equals 10, that's the expected distribution of the F statistic under the null hypothesis. It's the null hypothesis because each group was sampled from the same population. So I designed it because I did it, because I was in charge of these experiments. I could determine that the null hypothesis is true. And so what you see is most of the time you get pretty small F values, right? The bulk of the F values are really low, around 1 or less. But look at this. Occasionally, we get a couple of results where the F ratio is really large, almost 10. So that rare event, the F statistic is almost 10. That means I just happen to be so unlucky as to sample 10 here, 10 here, and 10 here. Right? Out of 1,000 simulated experiments, one of them was this unlucky situation. It's unlucky because if I ran my ANOVA, if this was my undergrad thesis, which I only do once, you're not going to do your thesis 1,000 times. You only do it once. If you're very unlucky, you would do your ANOVA on your data, and you run to your supervisor, and you tell her, holy crap, look at the effect that our drug had on memory in these mice. What if this was an animal model of Alzheimer's? And you're like, holy crap, I think we cured Alzheimer's in these mice. Look how big the F statistic is, right? You would compute a probability that could have occurred by chance. And the p-value would be like 0.00001. Actually, it'd be more like 0.001, 1 in 1,000, right? You say, and your supervisors, you say, it could be random sampling. You go, no, 1 in 1,000. It has to be the drug. It couldn't be random sampling. It's 1 in 1,000. Right? So it could happen. And my point in telling that story is, in these simulations, I designed it so the null hypothesis is true. When we do experiments out there in the world, you don't know. And in fact, you'll never know if the null hypothesis was true, and you were just really unlucky, or if the null hypothesis is false, and you actually did your Alzheimer's. You'll never know from that one experiment. All you can do is compute a p-value and hope that you weren't that unlucky. What could you do? Like, let's say that was your undergrad thesis, and then your supervisor said, well, holy crap, stay and do a master's, and let's explore this further. What could you do to convince yourself that wasn't, the p-value is one way of convincing yourself that wasn't just random chance. What else could you do to convince yourself that isn't random chance? Yeah.
Run either the same thing exactly the same or something similar.
Yeah, exactly. That's what I was looking for. Replication. Do the experiment again. Just simply do it again. Right? Doing it again would be like taking one of these other 999 values out of a hat at random. If the null hypothesis was true and you did that, then it'd be very unlikely you took that one. I mean, if your thesis, if your undergrad thesis was that experiment, and then your master's thesis was that one, you'd be really unlucky, right? More than likely, your master's experiment would pick one of these guys over here, and it'd be like a wah-wah. Okay, what went wrong? I must have done something wrong, right? And you run it a third time, and you pick one of these again, and you're like, oh man, how come I can't do this again? And maybe you get someone else in the lab to run it, or your supervisor phone up a colleague in England to run it in their lab, right? The more you replicate an experiment, the more certainty you have that it's real. So that's the distribution under the null. And let's say you did an experiment and you got an F statistic of 2.5, right? Let's say your thesis was actually an F value of 2.5. What you can do with this empirical distribution is you can simply count how many of those 1,000 null hypothesis simulations were as big or bigger as the one that I got in my actual experiment, 2.5. And you count and you say, well, 161 out of 1,000 were as bigger or bigger. And 161 divided by 1,000 is 0.161. So that's not less than 5%. So fail to reject the null, right? You can't reject the idea that, well, that 2.5 was just that big due to random chance. If your thesis gave you an F value of 1.5, it would be even worse. Your p-value would be almost 0.3. So you conclude, yeah, that's pretty likely that could have happened by random chance. So I can't reject it. If your thesis was such that it gave you an F value of 6, then you get a p-value of 0.038, right? And then you most likely conclude, well, I'm going to reject the null because I don't think I'm that lucky. Is that all that lucky? I don't know. Maybe 0.05, 1 in 20? No. In some labs, they demand 0.01, 1 in 100, to be sure. But even if your p-value is 0.01, it could be one piece. Yeah.
Sorry, so I'm just like trying to, because they talked about like the whole thesis thing. It's like, because you only do it once.
Yeah.
So then, how does that relate to the p-value stuff? Like,
yeah, so
you can't do your thesis 1,000 times.
No, you can't do your thesis 1,000 times. That's right. And so here I've generated this empirical distribution of F by doing these simulations 1,000 times. What actually happens when you get your p-value out of an ANOVA is it doesn't use an empirical distribution to get that p-value. It uses a theoretical approximation. Yeah, like a smooth curve. Remember when you did the Z distribution? It's that same idea. Yeah. There's a theoretical distribution of that. Given the number of groups and the number of samples in each group, you can there's an equation that gives you the shape, and there's an empirical, like an analytic expression that will give you the p-value. This is just sort of to demonstrate the mechanics of the idea behind it. Is there a question over here? No? All right. Okay, so that's what we get at the end of our ANOVA. We get a p-value, and I know this is maybe a bit repetitive and you've seen it before, but I think it's important to go through.
Sorry, I just had a question. So, kind of previously we learned about kind of like effect size in order to also see how, how applicable is it in the real world or practically. Is there anything kind of sort of for this, or would that have to be like post tests?
No, so the question is about effect sizes. For sure, there's a reading in the readings for this week on effect sizes. And you can absolutely compute an effect size in the context of ANOVA. And so just to recap what that means is, here we have a limited number of samples and a lot of intergroup variability. You would probably get a non-significant p-value, right? Because the within-group variance is big compared to the between-group variance. Now, what I kind of glossed over when I talked about the F ratio. Yeah, what I kind of glossed over is that The numerator and the denominator also include terms that relate to the number of samples within each group. So why that's important is if, imagine we had this same kind of situation as we do now with these particular differences between these, but instead of 15 subjects in each group, we had 1,000 people in each group. Right? The variability might be the same, but since we have 1,000 people, that gives us more certainty about our estimate of the mean of the population from which they came. And so the larger the sample size, the more certain we can be about smaller and smaller between group differences in means. And so that relates to effect size. You might get a very significant p-value if you had 1,000 participants in each group. And we'll talk about this later. That highly significant p-value doesn't necessarily mean it's a significant finding or a significant difference in the normal everyday use of the word significant. It doesn't mean it's an important difference, right? It could be a mathematically tiny difference between groups that's, quote, highly significant statistically. We'll talk about this a bit later, but I like to use the phrase statistically reliable instead of statistically significant, because the p-value really is a measure of how reliable, how certain you are that the differences are not due to chance. It's not really a measure of how big or important the differences are. So you could be developing a drug to cure Alzheimer's in an mouse model of Alzheimer's and test them on some memory task. And if you had 50,000 rats in each group, you might get a p-value of 0.0000001. And you write your Nature paper, a super highly mega significant difference, in memory with this drug. Whereas you actually look at how many items out of 100 the rats remembered, and in control they remembered 50, and with the drug they remembered 50 and a half. Right? It could be a tiny difference in the actual effect of the manipulation, but that tiny difference could be statistically significant because of how reliable you are that that difference is real. So it could be a real difference, and you're really certain it's real, but it could be really small.
That relates to the sensitivity of the test, right? And like power.
The power, yeah, that relates to the power of the test, which we'll talk about, I think, next time, after the midterm. Good questions, though. Okay, let's keep moving. So we talked about what the p-value of the x-test means. Like I said before, though, it tells you that the null hypothesis is not true. It doesn't tell you if it's not true which groups were sampled from populations that are different from which other populations. To do that, you need to do follow-up tests, and we're not going to talk about those this week. We'll talk about those not next week, the next class after the midterm. But the bottom line is the omnibus test is kind of like a gate that protects us. If the omnibus test says not significant, then it's basically saying, don't go looking for others, don't go comparing individual groups to each other. You could have 5 groups where 4 look the same and 1 looks a little different, and your p-value is 0.07. And you're like, 0.07. Not significant. That one looks different. I'm going to do a t-test between just those two. No. The omnibus test is telling you not to do that. It's telling you not to do that because it's saying, overall, those differences that are in there, there's a high chance that could be just due to random sample. The statistical concept in play is that omnibus test is protecting us from making type 1 errors. Well, making more type 1 errors than we want to. And we'll talk about that concept next week. Just quickly though, remember what a type 1 error is? Who remembers what a type 1 error is? Yeah? You want to say it?
The chance. So it's basically, I'm like thinking how the distribution looks. It's basically the chance of It's the opposite of power. It's basically if you run the test
Yeah.
and you find a significant result, even though
That's right.
it's not there.
Right. You make a type 1 error when you conclude that there is a difference when there actually isn't. So you make a type 1 error when the null hypothesis is true, and you incorrectly reject the null hypothesis. And so, what's the probability if the null hypothesis is true? What's the probability that you'll make a type 1 error? Yeah.
Usually 5%.
So usually 5%. Yeah, and what determines that 5%?
The alpha.
Yeah, the alpha, and what determines what alpha is?
Fisher.
Fisher, the statistician. Well, you do. The answer I'm looking for is, as an experimenter, you decide what your alpha level is, right? So you get a p-value out of your ANOVA, and then you have to decide, is that small enough that I'm going to reject the null or not? And so what's small enough? Well, the usual convention is 5%. Some people use a 1% cutoff. But the point is that you decide that. So the p-value out of an ANOVA is not the probability of making a type 1 error. The p-value is the probability of observing differences as big as you did if the null hypothesis is true. You only make an error, a type 1 or a type 2. You only make an error when you interpret the p-value, you make a conclusion. It's only when you reject the null or when you don't reject the null when you have the possibility of making an error. You can only make a type 1 error if the null hypothesis is true. Right? If the null hypothesis is false, you can't make a type 1 error. Right? You can make a different kind of error. You can make a type 2 error. A type 2 error is when the null hypothesis is false, but you incorrectly fail to reject it. In other words, you conclude there is no difference, but there actually is a difference. That's a type 2 error. But my point is, those errors are only produced when you make a decision based on the p-value. The p-value isn't the probability of the error. In fact, the alpha level is the probability of the type 1 error. And you decide that even before you run your experiment. Right? So even before you run your experiment, you know if the null hypothesis were true and you were to do your experiment 100 times, you've determined by making alpha 0.05 that 5% of the time you're going to make a type 1 error. If the null hypothesis is true. And like I said, you just run your thesis once. So is that one of the 5%? Maybe, maybe not. You'll never know. Or it might be the null hypothesis is false. You also don't know that. Okay, so we're going to talk about this idea of protecting us from making more type 1 errors next time, because it has to do with multiple comparisons. And the bottom line is type 1 error accumulates the more comparisons you make. And we'll see how that works next time. This is the ANOVA table that you probably, did you see that last term, that ANOVA table? That ugly thing? So you have sources of variability as rows, between groups, within groups, and then you have these different things, degrees of freedom, sum of squares, mean squares, the F ratio, and the p-value. That's kind of a standard format for the output of an ANOVA. And you kind of work backwards. The p-value is based on the F statistic. The F statistic is based on the mean squared between divided by mean squared within. Mean squared between is sum of squares between divided by degrees of freedom between. And likewise, mean squared within is sum of squares within over degrees of freedom within. What's sum of squares? Between is the sum over all groups of each group mean minus the grand mean of all groups squared multiplied by the number of subjects in each group. And the within group sum of squares is the difference between each observation and its group mean squared and summed together over all groups. And then degrees of freedom within is the number of observations minus the number of groups. and between is the number of groups minus 1. So you can kind of play games with the math here. Imagine that you have more participants versus fewer participants, but everything else is the same. How's the F ratio going to change? Or everything's the same, but you have more within variance or less variance, or more between variance or less between variance. How's the F ratio going to change? They discuss that in the textbook a little bit. So read that chapter for that stuff, and also for a worked example with actual numbers. In the old days when I took stats, we were shown this table, and then we were given like a page of numbers, pencil and skill. Compute that, and then how do you get the p-value from that? I don't know if you've ever seen it, but in old stats textbooks, they're like 800 pages long. And the last 200 pages are just tables and tables and tables of p-values that correspond to like this many degrees of freedom numerator, this many denominator, and so you like flip to the right page and then this giant table of values, and you're like, okay, that many here and this many here. 0.048. It was good times. So we're not going to do that at all. We're just going to rely on R to give us the p-value, and in fact, to give us this whole table. So I'm not going to ever ask you on an exam to do those calculations or to do anything tricky with those terms. But it is important for you to look at them in the chapter and understand how it works. Open the hood of your car and sort of understand how the engine actually kind of works. Then close it up and just drive. You don't need to worry about it again.